Hello, welcome to our channel for probability and statistics. In this video, we will talk about using analysis of variance approach or ANOVA approach to analyze the linear regression model. So say we have a simple linear regression y with independent variable x. So one aspect of analyzing or evaluating the model's explanatory power is to check the variance explained by the model and not explained by the model. So this approach is called analysis of variance approach. So we will subdivide the total variance of the dependent variable into parts. So first we say from the linear regression estimation we can get this equation SYY equals B1 times SXY plus SSE. Here B1 is the slope parameter coefficient, and if we look at notations in linear regression, SXX is the sum of x against its mean value take square, and SXY is the sum of the cross product of x and y against their mean and take square, and then take sum, right? And SSE actually is the error term between the observations of y and the fitted value of y. So this is the fitted value of the y. So this error term takes square and takes sum, we call SSE. So SSE equals SYY minus B1 SXY. So if we go further, we will write in this form. So SST is the total variance of y against its mean, take square and take sum. And SSR, called regression sum of squares, actually is the fitted line. It's the fitted line minus the y mean values take square, then take sum. And the last term called SSE is the regression sum of the sum of the squared errors. So this term is the sum of squares of the error term, which is between the opposite of the value and fitted value. So this equation called partition of total variance in the regression. So SST equals SSR plus SSE. So we can look at this table. This is ANOVA table, analysis of variance for the linear regression. So SST equals SSR plus SSE. And then each term have their corresponding degrees of freedom. And we can form and null hypothesis that beta 1 is 0. So beta 1 is 0 means this model does not exist. Actually, no explanatory power for the x variable for the y dependent variable. So this is the null hypothesis. And against an alternative hypothesis, beta 1 not equal to 0. So we will use this ANOVA table, then form an F-statistic, which is a division of SSR by the SSE and their corresponding degrees of freedom in the denominator. So this actually is SSR divided by S squared, because SSE divided by n minus 2 divided by its degrees of freedom called S squared. S squared is an unbiased estimate for the model's variance, for the y variable's variance. So we have this f value. So just if this computed f statistic exceeds the critical value in F distributions density curve with 1 and n minus 2 degrees of freedom, then we will conclude that there is a significant amount of variation in the response accounted for by the postulated model. So this model is the regression line. And on the other side, if F-statistic is in the field to reject, then we will conclude that the model or the data did not reflect sufficient evidence to support the model postulated. So this F-test is to say we test this model by total, because this model has only one independent variable. So this is the same as we test beta when is 0 or not 0. So if this model is multiple linear regression with more than one independent variable, and F-test approach or analysis-of-variance approach can also apply. So this also says if the significance of the F-test, which means in the combination of these couple of independent variables, has explanatory power for the model to estimate the dependent variable. So this is command summon for F-test. But for the simple linear regression with single independent variable, F-test equal to a t-test for the beta when 0 against the beta when not 0. Because in a single variable, the t-test statistic take a square exactly equals to the F-test. So this is just another alternative approach to the t-test for the beta when not equal to 0. Thanks for watching.